Well, why hello YouTube. I'm back on the no grass grind, and today we will be going over another episode of an intro to complex analysis. Today we'll cover Cauchy's theorem, Cauchy's integral formulas for finding integrals in the complex plane, and applications. So, like, how would Cauchy's integral formulas apply to, say, the integral from 0 to infinity of 1 over x squared plus 1 squared dx. In ordinary calculus, there's no techniques to integrate this. Like, integration by parts doesn't work, there's no u sub. So you have to use complex analysis to compute this integral, and I'll show you how later. Alright, so let's cover Cauchy's theorem first. So what Cauchy's theorem states is that a closed line integral of f of z dz is equal to 0, provided that the domain that f of z encapsulates is analytic. So I'm assuming you know what a closed line integral is already. Basically, let's say you have this like weird shape. As long as it makes a full revolution around whatever this is, and it's closed, there's no gaps leading to the outside. So if this area is domain D, it has to be analytic throughout, which means that it must be infinitely differentiable, continuous, whatever. So if f of z equal 1 over z, Cauchy's theorem could not apply here because there would be a discontinuity at z equals 0, right? Oh, I forgot to label my axes. It would not be continuous there or differentiable at that point. Therefore, f of z is not analytic throughout the domain D. So before we move on to Cauchy's integral formulas, let's do a practice problem for Cauchy's theorem. So let's say we have a unit circle on the complex plane of radius 2 centered at I. Now, let's say we have a function f of z that's equal to 1 over z minus 2. My question is, what is the closed line integral of f of z throughout this unit circle? Well, in order to find that, we need to plot out the discontinuity, which we're not quite sure where it stems or where it is with respect to this circle, but what we do know is that there's an angle theta here, and this is a non-zero angle, which means that this side length over here, which I'll just call L, is equal to r cosine theta, or 2 cosine theta. And since theta is non-zero, we know it's going to be less than 2, because in a right triangle, the adjacent side to the angle is always less than the hypotenuse. So we know that this distance L is less than 2, meaning that our discontinuity z equals 2, it has to be somewhere outside of the unit circle. Therefore, Cauchy's formula does apply, or Cauchy's theorem does apply, because the only discontinuity that f of z has is outside of the circle, meaning that the domain D is analytic throughout this entire closed curve. Therefore, the closed line integral of f of z is equal to 0. Okay, let's move on to Cauchy's integral formula number 1. So, our formula, I'll just give it to you before showing you the application, just so it's simpler. So, our formula is f of z naught equals 1 over 2 pi I times the closed line integral of f of z over z minus z naught dz, assuming that the closed curve encapsulates z equals z naught, where z naught is our discontinuity. So let me just give a practice problem to show what all this means, because this is very difficult to digest. You're probably thinking, what the hell are you talking about? So let's say we have this, I don't know, closed curve, and we have a discontinuity at z equals 0. Well, shoot. It looks like we can't just set this equal to 0, because our discontinuity is inside our curve, meaning that our domain D is not analytic. So we have to use Cauchy's integral formula to solve it. So for practice problem's sake, let me just assign a integral to solve. So let's say we want to solve the line integral of e to the z over z, since z equals 0 in this instance, dz. I'll just put minus 0, just so you know what I'm talking about. So here, our f of z is equal to e to the z power, because we have our z minus 0 here, which is this part of the formula. So f of z 0 equals 1 over 2 pi I, closed line integral of f of z, z minus z0 dz. So we can use some algebra here, get 2 pi I times f of z naught equals to our line integral, which I'll just write here. And now we could just start substituting things out. So f of z is equal to e to the z power. So we get 2 pi e to the z naught power equals to the closed line integral of e to the z over z dz. Then, well, the denominator comes in the form of z minus 0. So z has to be 0, or z naught has to be 0 for there to be a discontinuity. So we would get 2 pi I e to the 0 equals that integral, which I'm not going to write again. So that just equals 2 pi I. And this basically confirms the result of the solution that I posted in one of the previous videos I did on complex analysis. But this time we have like an actual formula that backs it up.